guys are working on some nice stuffs.
Yeah, let's
Make our students future ready and all, and I really like the idea how the students here are working on different things, on new technologies,
and felt the subtitles truly capture the scene. And Netflix pulls this off in 30 plus language. You are scrolling through Spotify. The lyrics may be foreign, they align perfectly with your taste. Understanding and applying text embeddings, semantic search and document clustering to anomaly detection, few shot learning and cross-modal matching. अब नहीं रुका जा सकता. Now we cannot be stopped. Have you ever watched a native language show on Netflix, say Sacred Games, and felt the subtitles truly capture the scene? They are not just literal translations, they carry the emotion behind the words, the tone of the speaker, or even the cultural nuance of the scene. And Netflix pulls this off in 30 plus language every single day. So how does a machine decide that the Hindi language, let's say, अब नहीं रुका जा सकता, should read, we can't stop now, rather than a literal, now we cannot be stopped? It's not brute force translation, it's meaning matching. Or let's say you are scrolling through Spotify and out pops a song in a different language, one you never heard, yet it hits the same chill vibes as your go-to playlist. The lyrics may be foreign, but the feel, the rhythm and emotion, they align perfectly with your taste. How does Netflix or Spotify do it? It's not matching waveform or keywords. It's comparing embedding vectors, rich numerical representations of audio features, lyrics, and listener behavior. So you get recommendation that feels right. Hey, I'm Stuti Gupta, data scientist at Flipkart, and in this masterclass, we'll cover understanding and applying text embeddings in LLM systems. Today, we'll pull back the curtains on these high-dimensional vectors and see how they transform raw text into semantic gold. By the end of this session, you will be able to convert words, sentences, and documents into dense vectors that encode meaning. Visualize and reason about semantic similarity. Think of it as a mapping idea in a hidden landscape. Distinguish between static and contextual embeddings and witness how transformers give context its magic. Apply embedding to real-world challenges from intelligent search and clustering to sentiment classifications. Whether you are engineering a best-in-class recommendation engine or building chatbots that truly understands user intent, embeddings are the foundation you can't afford to skip. Now, before we begin the session, let's review the prerequisites you should have to follow along and get most out of this session. Python and Jupyter Notebook, OpenAI API credentials, and ChromaDB. AI doesn't read the text the way we do. Under the hood, it only speaks in number. So how does we teach a machine that love and affection are related but love and rocket have nothing in common? The answer is embeddings, dense vector that bridges human language and machine computation. Embeddings solve this by mapping each token or entire sentence into a point in a high-dimensional space. For instance, here I have shown embeddings of cat, kitten, and rocket. Cat, as you can see, the vectors 0.19, minus 0.32, and for kitten it's 0.21, minus 0.30, and for rocket it's minus 0.45, 0.77, and so on. And as you can see, the vectors of cat and kitten land close together because they share similar context during training. Meanwhile, rocket, used in a very different context, ends up across space. Now, why numbers? Computers excel at linear algebra, matrix multiplication, dot product, vector norms, etc. By converting text into numerical vectors, embeddings unlock a toolbox of mathematical operation. Similarity, how close are these points? Cosine and Euclidean distance are used. Clustering, group nearby points, k-means and hierarchical clusterings are used. Classification, which region of space, logistic regression and trees are used. Think of embedding as the DNA of your text, compact, unique codes that carry meaning across every downstream task, from search and clustering to recommendations and sentiment analysis. And these tiny vectors power modern AI. Netflix matches subtitles to emotional nuances across 30 plus language. Google search rank results by semantic relevance, not just by keyword hits. Spotify recommends fresh tracks by comparing lyrical and acoustic embeddings. ChatGPT follows complex instruction because it reasons over sentence embeddings. Without embedding, large language models are nothing more than sophisticated token counters. With embeddings, they truly grasp the meaning. Now that you understand why embedding matter and what they are, we are ready to create them ourselves. We'll generate our first embedding vectors, inspect their shape, and lay the groundwork of everything that follows onwards. In this lab, we'll generate embeddings for simple inputs like the word cat or a short sentence using the OpenAI Embedding API. Let's dive in. So we'll start with importing the necessary library. For the first exercise, the important library that we need is OpenAI. Then next, we will define the OpenAI API key, and now we will generate embedding for a given word. So for that, I have here written a function get OpenAI embeddings, which accepts the text or basically the word that you are going to pass, and this parameter describes the model that I'm using. So here I'm using text embedding 3 small model of OpenAI to generate the embedding of the word. In the next line, I'm calling embedding.create function of OpenAI, where I'm inputting the text and the model that I'm using. Finally, I'm returning the embedding from the response variable that I have used to store the embeddings. So in the next cell, I have assigned the word cat to the variable word here. Next here, I'm calling the function that I have created and I'm passing the word here that we have defined, that is cat. And I'm storing the embeddings in the variable embedding cat. Let me run this. Okay, now we have the embedding for the cat variable. So let's print and see how it looks like. So as you can see, it has returned an array. Let us see the dimension of the array that has been returned. So here we have got 2-dimension array. Let us just check the shape of the embedding cat array. What do you guys think? What will be the shape? So the shape here is 1 by 1536. What does it mean? So here 1536 is actually the length of the embedding vector that the model has returned. So far we have seen the embedding of one word, that is cat. Now let me change that to a sentence and show you how that embedding turns out to be. Okay, so I am here changing cat to a word, say cat are cute. Let me rerun this. I am again passing that word in my function. And if I print the output of embedding cat, it has changed. I think you guys have observed that. Now tell me what will be the dimension of this sentence, cats are cute. Okay, I think you might have guessed it right. It will remain the same, that is 2. And what do you guys think? Will the shape change? Let me just run and show it to you guys. Oh, it remains same because the entire sentence has been used by the model to generate the embeddings. In the first lab, we have learned how to create embeddings. Now let's zoom in on how embedding actually encode meaning. To keep things tangible, we will use 7-dimensional toy example. Each dimension represents an abstract trait such as is living being, is feline, is human, is royal, is verb, or is plural. For instance, our toy vector look like this. So here you can see the cat has an embedding vector which reads like 0.6, 0.9, 0.1 and so on. The kitten embedding has a vector which reads like 0.5, 0.8, minus 0.1 and so on. So the dog embedding vector reads like 0.7, minus 0.1, 0.4 and so on. You can see cat and kitten both scores high on living being and feline, while houses is non-living being, negative on that axis but strongly plural. Now, when we reduce this 7-dimension points to 2D, for example via PCA or TSNE, we get a visualization like this. Cat and kitten cluster tightly together. Dog sits nearby, also a living being but not a feline. And houses drifts far off in its own region. This simple map reveals both lexical similarity between cat and kitten and conceptual distance between cat and houses. In real embeddings, we are not limited to 7 dimensions. You might have 100 or even thousands of dimensions. Each dimension is a learned feature capturing nuances like sentiment polarity, happy versus sad, formality, hello versus greeting, topic domain, finance versus sports. Because these features are distributed across so many dimensions, meaning emerges from collective pattern, not a single dimension. When you plot real-world embeddings, say thousands of product descriptions, news headlines, or customer reviews, you'll see clear clusters of related concepts. Animals grouped in one region, action verb in another, and technology terms over here. And that's how machine can in milliseconds identify that laptop belongs with wireless or that digital keywords deserve grouping under a technology theme, even if the exact words differ. Now think about your own domain. What categories or themes do you expect to emerge if you plot your data's embedding? That visual intuition is what makes embedding so powerful and why mastering them is the key to unlocking semantic search, recommendation engine and beyond. So in this lab, we will be creating similar charts that we have seen above. Okay, we'll start with a small data set. Here, I have taken a list of 11 words. Let me just run this cell. Okay. Here, you can see that the length of words returned 11 because we have this 11 list of words. Now here, what I'm doing is I'm calling the same function that we have used above, and I'm passing here the word list to get the embeddings of these words. I'll run this. Now let me print the embedding of these words. So here is the embedding of these 11 words. So what do you guys think? What will be the dimension of this embedding vector? I hope you guys have guessed it right. It's a 2-dimension vector. Now let me print the shape. But before printing, take a guess what will be the shape of this embedding vector. I hope you guys have guessed it right. It's 11 cross 1536. Here 11 is because we have 11 words and each word has a dimension of 1536. Now let's try to plot this embedding vectors on a chart. But since it is of dimension 1536, we can't plot it directly. So before that, we will convert the 1536 dimension to 2D so that we can plot it easily. Here, I'm basically converting the embeddings into 2 dimensions and plotting it in a graph. In the chart, you can clearly visible how the cat and kittens have grouped together as we have seen in the picture, and the man, boy, girl and women grouped together, and how these words are far apart from car, bike, truck, which are not related to these words. Now, we have seen this on a small data set. Let's build the same thing on a large data set. So here I have taken a list of unique words. I am reading that list of unique words in my data frame. Let me show you how the data frame looks like. So as you can see, it is just a list of unique words that I have in this data frame. Let me print the shape to give you an idea how big the data is. So we have 109 rows in this data frame. Here I have modified the embedding function a little bit. So in above function, we were passing these words and getting the embedding. But since now Here we have large data set. I'm using batch size to basically process it one by one. I'll run this function, and this function has returned the embedding of this entire list of words. Now I'll do the same thing. I'll visualize it using UMap. So now I have 2-dimension embedding of these vectors. So let's now plot and see how it looks like. So I'm running this plot function and whoa, you can see how words have arranged themselves. Are you able to find clusters in this? Of course, I can find. So you can see here one cluster which is related to all gadgets. The other cluster that I can find is this one, which is related to all the locations. And the third one that I can clearly see is this one, which is basically showing us the colors. Okay, now I guess you guys have an idea what embedding looks like and how it will look on a chart when we will plot it. Up to now, we have treated embeddings as a single concept, but there are two very different flavors, static and contextual. Choosing the right type can make or break your application. So let's unpack each one. Static embedding algorithms like word2vec and glow assign one fixed vector per word, regardless of whether the word appears in a finance article or a nature documentary. For example, word2vec might map bank to a vector that reads 0.12 minus 0.34, 0.88 and so on. No matter what sentence it is in. These words comes from co-occurrence statistics across massive corpora. The pros of static embeddings are fast and light. You simply look up the vector in a table, perfect for real-time search indexes. Easy to scale, static vectors can be pre-computed for your entire vocabulary. The cons of static embedding are polysemy blindness. The word bank in the river bank and investment bank share the same vector, leading to mistaken similarities. Context ignorance. They capture general meaning but can't adapt to new context or idioms. The contextual embeddings are powered by models like Elmo, BERT, and GPT. Here, each occurrence of a word produces a unique vector influenced by its surrounding words. In river bank, bank might map to a vector which reads as minus 0.45, 0.72, minus 0.11, which is leaning towards a natural context. In investment bank, it shifts to a vector which reads as 0.31, minus 0.08, 0.95, which is leaning towards a finance territory. The pros of contextual embeddings are disambiguation. Polysemy dissolves word morph to fit their sentence. Nuanced understanding. Idioms, slangs, and rare senses are captured dynamically. The cons of contextual embeddings are compute intensive. You must run the full transformer stack to get each embedding. Latency and cost. Real-time applications may struggle with the overhead, especially at scale. In practice, static embedding shine in large-scale search, fast similarity lookups, and resource-constrained environment. Think semantic search over millions of product titles. Contextual embeddings power deep understanding in chatbots, summarizers, and any task where nuance and disambiguation matter, like extracting meaning from legal contracts or medical notes. With this clarity, you are ready to harness both static and contextual embeddings, mixing and matching to optimize performance, cost, and accuracy. Next, we'll peek under the hood at how transformers create those context-aware vectors. Now that we have seen the power of contextual embedding, let's peek under the hood at how transformers actually produce them. It happens in 4 core steps, each one critical to giving words their contextual aware meaning. First, we tokenize. Break the sentence into words or subword tokens. Let's take the sentence, the bank approved. This will break into the tokens, the, bank, and approved will be broken into AP and proved. And each token will map to a numeric token ID. Then we do a quick lookup. Each ID retrieves a base embedding, the same static vector we discussed earlier. This gives us our initial guess for each token's meaning. Next comes the magic, self-attention. Each token looks at all the other and assign a weight to each connection, essentially asking how relevant is that token to me right now. In River Bank, the token bank places more weight on the river. In investment bank, it shifts weight towards investment. By taking a weighted sum of its neighbor's vector, each token refines its own representation to reflect the contextual relationship in the sentence. After attention, each token's context-aware vector passes through a feed-forward neural network, a mini neural net that applies non-linear transformation. Think of this as the model polishing the rough draft of each token's meaning, sharpening pattern that attention uncovered. Finally, we stack these self-attentions plus feed-forward blocks repeatedly, anywhere from 12 layers in both base to 96 layers in the largest GPT models. Each layer refines the token's embedding further, capturing deeper and more abstract relationship. By the end, every token's vector is a rich, context-aware embedding that carries nuance, disambiguation, and even subtle stylist cues. And that's the transformer recipe for contextual embeddings in a nutshell. Armed with this knowledge, you are ready to experiment, swap layers, tweak attention heads, and see how your embedding shifts. Next up, we'll explore real-world applications where these context-aware vectors make all the difference. We have seen embeddings powering flawless subtitles and spot-on song recommendations, but their superpower stretches far beyond entertainment. Let's explore 5 real-world applications where embedding turns messy human inputs into structured, actionable signals. In semantic search, embedding lets you match queries to catalog items, even when keywords don't align. Instead of literal string matching, the system compares vectors. Comfortable walking sneakers and cushioned walking shoes land in the same semantic neighborhood. This raises relevance, reduces zero result pages, and delights customer. Second, document clustering. Imagine shifting through tens of thousands of support tickets every day. With document clustering, you embed each ticket's text and lets unsupervised algorithms like k-means group them by theme. In anomaly detection, you learn the embedding signature of normal behavior, API calls, error messages, transaction patterns. When a new log's embedding falls far from the norm, you get an immediate alert. It's like having a guard dog that senses when something weird is happening in your system. Few-shot learning lets you adapt models on the fly with minimal label data. You embed a handful of examples, say 3 positives and 3 negative product reviews, then include their embeddings in your prompt. The model generalizes to new reviews, classifying sentiments without full retraining. Finally, cross-modal matching aligns embedding across text, images, and audio. Want to find product descriptions that match an uploaded design sketch or retrieve video clips that match a podcast transcript? By projecting different modalities into shared embedding space, you unlock powerful multimodal search and recommendations. Whether you are in e-commerce fine-tuning your search bar, in finance clustering compliance documents, in healthcare triaging patient records, or in media matching scripts to footage, embeddings translate human language into machine-readable signals. Embeddings aren't just a cool trick. They are the backbone of intelligent, scalable systems that understand meaning at scale. Alright, time to put embeddings to the test in a classical machine learning scenario. Sentiment classification. Imagine you run a streaming service and want to automatically label each new movie review as positive, neutral, or negative. This helps you improve recommendation, promote popular films, and find movies that need more marketing support. Embedding gives you a powerful, low-code, way to turn text into features for any standard classifier. The prerequisites for this are: first, label feedback dataset, so short text tagged as positive, neutral or negative. Second, embedding generator. We will reuse our lab 1 code to convert each sentence into a fixed length vector. Then third, we'll need ML library, so we will use scikit-learn, XGBoost or your favorite toolkit installed. The workflow going to be: embed each movie review into its numeric vectors, split the data into train and test sets, example 80-20 split, train an XGBoost classifier over the embeddings, and last, evaluate on the test set, then inspect misclassifications to uncover embedding blind spots such as sarcasm, domain jargon, etc. In the hands-on lab, I'll walk you through each step: loading data, calling the embedding API, fitting the model, and interpreting results. For now, keep in mind embeddings often make your classifier more robust to vocabulary drift and help it generalize to phrasing it hasn't seen before. Ready to see it in action? Let's switch to the notebook. So here in this notebook, I have actually taken IMDb dataset. I'll just run this file where I'm defining the file path. And then in the next cell, I'm reading this file and fetching only 10,000 records for fast processing. Let's see the shape of this dataset. So it has 1000 rows and 2 columns. Let's see it visually how the data looks like. So as you can see, the 2 columns are review and sentiment. The review has all the text and sentiment is giving us the label. Let us check the unique sentiments that we have in this dataset. So we have 2 sentiments, positive and negative. Next, what I'll do is I'll use the same function that I've used in my previous lab and will create embedding for this review column that we have in the dataset. And in the second line, what I'm doing is I'm mapping the negative and positive to 0 and 1 labels. I'll run this. Okay, it has completed. So now we have X and Y. Let's split it into train and test. So here I'm using 80-20 split. Okay, here I have used XGBoost classifier to train my embeddings. Next, here I'm evaluating the model. So I'm calling the predict function and passing my test dataset and storing the results in ypredict. Let's see how the model has performed. So as you can see, the classification results are really good. Let's now see on a sample of text. So here I have defined a function which will take the text and will give us the sentiment. Here I have taken the sentence, the film was beautifully directed and emotional. Let's run and see what our model will predict the sentiment. Okay, it has predicted positive. So this is how you have seen how we have used the embeddings in classification and was successfully able to classify the sentiment of the movie reviews. So now I will be showcasing how to build semantic search. I will be showing you 2 methodology, one using cosine similarity and other we will be using a vector database to build this semantic search. Starting with the cosine similarity, I have taken a small dataset here. It's a dummy dataset of FAQs. So in the next cell, we are basically using the same embedding function and passing this FAQs and getting their embeddings. Okay. Now I have taken a new query which reads, I can't pay for the subscription. What I'm doing here is, I am generating the embedding for that query and then I'm using cosine similarity to basically calculate the cosine similarity between the query embedding and the FAQ text that we have. And then here I'm taking the top 2 FAQs that has matched with my queries. So let me run this cell and let's see what 2 FAQs matched with this query that I have given. So as you can see, the query that we have given was I can't pay for the subscription, and the 2 matches that has been returned from the FAQs are payment failed while purchasing the plan and guide to fix payment failure issues. Isn't these 2 very relevant? So that is where the power of embeddings lies. Now I think you have a fair idea what we are trying to achieve in semantic search. Let's implement semantic search using a vector DB. Here I'm using ChromaDB for this, and let me give you a brief what I'm trying to achieve here. So I have a files which has information of pet, so I'll be using those files and converting their text into embeddings, and then we'll use those embeddings to get output against the queries that we will be going to give. So let's start first. We'll create a Chroma client instance. Here I'm reading the pet files that I've just mentioned. Let me show you the file data. So as you can see in the file data, I have the file names. As I mentioned that I have multiple files regarding these pets, and then I have content against these files. So here is the code where I am converting the content of the files into their embeddings and storing. And here you will find also the code where I am creating basically a collection of embeddings in my vector DB. So let me walk you through the code. Here I am basically enumerating through my file data, then I am appending my data content in this document variable. Here I am first converting my data content into embeddings and then appending that embeddings in my embedding vectors. Then I am creating metadata where I am appending the source, which has nothing but file name. And finally I am appending the IDs of these files. In the next line, I am basically creating a collection in vector DB with the name pet collection embedding 2, and in the last line I am adding these documents embedding metadata and IDs that I have generated. Let me run this cell. So now our vector DB is ready with the embeddings and the content. We can now use our vector DB to search against the queries. First query that I have given is what are the different kinds of pets people commonly own? Let's see if it will be able to fetch a relevant content from our vector DB. So as you can see, the content that has returned, which says pet animals come in all shapes and sizes, each suited to different lifestyle and home environment and so on. This is quite relevant, right? Let's take another question. How to take care of the dogs? Let's see if my embedding vector will give relevant results this time also. Let me run the code to find it out. Okay, so the response that has been returned reads, routine healthcare is crucial for pets to live long, happy lives and so on. Isn't it also relevant? So now you have seen how these semantic searches help us build a semantic search engine which basically takes query and returns relevant documents or content from the DB. In the last lab, we have seen how semantic search is implemented. And believe me, this is how searches takes place in e-commerce platform. Of course, there is a lot in top, but the base is semantic search. We have taken quite the journey today. We started with the humble idea that AI only understands number, then introduced embeddings, those dense vectors that let machine grasp meaning. We dug into a 7-dimensional toy example, saw real-world clusters emerge, and learned how static and contextual embedding serves different needs. We even peeked under the hood at transformers, unpacking the 4-stage processes tokenization, self-attention, feed-forward layers, and stacking that creates context-aware representations. Then we explored a range of applications from semantic search and document clustering to anomaly detection, few-shot learning, and cross-modal matching. Finally, you saw how to plug embeddings into a classic sentiment classifier, turning text into features that power your model. So, the key takeaways from this session are embeddings are the lingua franca bridging human language and machine computations. Visualization reveals hidden semantic structure, your shortcut to intuition. Static versus contextual embeddings. Choose based on speed, scale, and the need for nuance. Transformers are the engines behind dynamic, context-sensitive vectors. Your next steps will be revisit the lab, run them end-to-end. Experiment with your own datasets such as tweets, logs, product reviews. Explore fine-tuning and RAG workflows to inject domain knowledge. Embeddings have transformed the way AI understands language, and they are only getting more powerful. I can't wait to see what you build next. Thank you for joining Understanding and Applying Text Embedding in LLM Systems. Until next time, let's keep pushing the boundaries of how AI grasps meaning, one vector at a time.